In my last video, I made soap from oil, but while I was working on it, I wondered if it was possible to do the reverse reaction, as in make oil from soap. I thought that the coolest thing I could do would be to take soap, convert it back to oil, and then cook some French fries. In my little fantasy, I imagined eating the fries, but I knew that it probably wouldn't be a good idea. Anyway, this video is mostly just for fun and to explore the science behind this conversion. Making soap from oil is very straightforward and surprisingly easy, but going backwards is a lot harder. Based on my research, this process is more than possible to do, but just as a disclaimer before we start, I wasn't able to get it working. However, despite it failing, I still thought this whole concept of going in reverse could make an interesting video. I'm just going to do a quick recap of the normal soap making reaction that we saw in the last video. It starts off with oil or fat, both of which are made almost entirely of triglycerides. The triglyceride molecule is composed of a glycerol backbone connected to 3 fatty acids. The bonds between the fatty acids and the glycerol are known as ester bonds, and they're somewhat sensitive. If I mix a strong base with triglycerides, the ester bonds can be broken, releasing glycerol and salted fatty acids. These salted fatty acids are pretty much what soap is. If I want to do this reaction in reverse, I'm going to have to put the triglyceride back together and remake all of the ester bonds. Unfortunately, as with most things, putting it back together is a much harder task. The sodium salted fatty acids are first converted back to regular fatty acids, and then they're reacted with glycerol to remake the ester bonds. When I word it like this, it sounds relatively easy to do, but it's actually a lot trickier. Anyway, to get this project rolling, the first thing that I'm going to need is some soap. The biggest issue with most soaps, including mine, is that they're made from a mixture of oils, so there's a lot of different fatty acids in there. Even if I were able to flawlessly attach all of the fatty acids back to glycerol, I can't really control which fatty acids go where. For example, the major fatty acids that make up olive oil are oleic acid, linoleic acid, and palmitic acid. The major ones that make up coconut oil are lauric acid, myristic acid, palmitic acid, and a bunch of others. The triglycerides that would form from the reaction would be a mixture of all of these fatty acids. A lot of them would contain both lauric and oleic acid, so they'd be kind of a hybrid between the two oils. This would make the final product very hard to predict, and it would make things really messy and hard to purify. So to make things reasonable, I'm going to need to use a soap that's made from just one oil. As I said before, my soap is made from a mixture of coconut oil and olive oil, so unfortunately I can't use it. Also, most commercial soaps are a mixture or have a lot of additives. With a little research though, I managed to find a bar of soap that claims to be made from pure olive oil. It also says that it has no additives, colorants, or anything, so it seems to be ideal for my purpose. Okay, to start things off, I need to grind up the soap. I decided to do it manually using a cheese grater, but there's probably an easier and more automated method. In the next step, I need to dissolve all of the soap into water, and powderizing it first makes it go way faster. It is possible to just chop the soap up into smaller pieces, but if you do this, be prepared for a long and painful dissolving process. After a lot of pain and effort, this is what I'm eventually left with. All the soap was then added to some distilled water. I mixed it around and let it stir on its own for about 10 minutes, hoping that everything would dissolve. All of the powdered soap disappeared pretty quickly, but there were still some chunks floating around. These were larger pieces that I wasn't able to grind up very well, but I decided to include anyway. In hindsight, I probably should have just chucked them out, but in any case, I need to deal with them now. At room temperature, it was taking forever to dissolve, so I heated it up a little in the microwave. After a little bit of warming and a lot of stirring, everything eventually dissolved and we're ready to add the acid. When the hydrochloric acid is added, it immediately reacts with the salted fatty acids and converts them back to their unsalted form. The sodium chloride side product is just going to dissolve into the water, but the fatty acids are insoluble, so they're going to separate and float to the top. The idea here is to keep adding hydrochloric acid until I get to a pH of around 1 or 2. This is definitely overkill, but by making things really acidic, we can be sure that we've reacted everything. After I got to my target pH, I continued to let things stir for about 10 or 15 minutes. When I come back and I take the beaker off the stir plate, the fatty acids quickly start floating to the top. Adding the hydrochloric acid caused things to heat up a little, so now it's time to wait for it to cool. When the solution is warm, most of the fatty acids are liquid, but as it cools, a lot of them will solidify. When it gets to around room temperature, the entire beaker is placed in a fridge. I left it in the fridge for a couple hours, and when I take it out, the fatty acids have completely solidified. I take out the glass rod, and then using a metal spatula, I separate the fatty acids from the beaker. It can be removed as one large chunk, but I recommend cutting it into smaller pieces. All of the fatty acids are then scooped out and dumped into another beaker. The liquid that's left over contains excess hydrochloric acid and sodium chloride. To get rid of it, it can just be poured down the drain with a bunch of extra water. If I were doing this with homemade olive oil soap, the water would also contain glycerol. However, because it's a commercial soap, the glycerol has been removed. Just to confirm this, I boiled down all of the water, and I was left with just some dirty sodium chloride. When I first started this project, I was really hoping that the glycerol would just magically still be in there, even though it's not listed on the ingredients. The idea of isolating both the glycerol and the fatty acids from the soap, and then recombining them to make the oil, seemed really cool to me, but unfortunately, I'm gonna have to use store-bought glycerol. Anyway, moving on, these are the fatty acids that I've isolated. In theory, they should be colorless or white, but for some reason they're green. The label said there were no dyes or colorants present, so I guess the olive oil that was used to make the soap was just not super pure. This is not at all to say that the olive oil they used was bad, it just means that it wasn't heavily refined. Anyway, now I need to connect them to glycerol to make triglycerides. The typical way to do this is to react the fatty acids with glycerol at a high temperature in the presence of a base or acid catalyst. With a little bit of research, I found a paper that described using zinc chloride as the acid catalyst, and they tested a whole bunch of different reaction conditions. It was really convenient for me, and they gave the optimal conditions to make the triglycerides. So to get things started, I turn the hot plate to a low heat, and I melt the fatty acids. Then, when everything's a liquid, I start to add the glycerol. When I'm done adding the glycerol, I dump in the zinc chloride. The amount of catalyst that I use is just based on the mass of the fatty acids, but the amount of glycerol that I need is a little bit harder to calculate. I have no idea the exact composition of fatty acids I have here, so I had to assume that it was all oleic acid. Oleic acid is the most abundant fatty acid in olive oil, but it definitely doesn't represent 100%, so the numbers are going to be a little bit skewed. The amount of glycerol that I calculate is going to be slightly lower than it should be, but this isn't really a problem. For this reaction, I actually want to use less glycerol than is needed to make sure that the fatty acids stay in excess. This way, we can really promote the formation of triglycerides over things like diglycerides or monoglycerides. So, on top of the already low glycerol estimate, I knocked off another 10%. Anyway, once everything's added, I crank up the heat. I start to get a little bit worried about splashing though, so just to be safe, I transfer everything to an Erlenmeyer flask. The goal now is to heat everything to 195°C and to hold it there for 100 minutes. So in theory, this is the reaction that should be going on. In the presence of an acid catalyst, the glycerol reacts with three fatty acids to form the corresponding triglyceride and water as a side product. The one unfortunate thing is that acid-catalyzed ester formation is an equilibrium reaction. So the water that forms can go back and hydrolyze the ester and take the reaction in the reverse direction. The major way that we're getting around this is by doing the reaction at a really high temperature. At nearly 200 degrees Celsius, any water that forms will be almost immediately boiled off. Without the water, the reaction can't go backwards, and everything should slowly be funneled to the products. So in terms of the mechanism, it's a pretty typical acid-catalyzed ester formation, and I'm just going to quickly cover what's going on. In the first step, the fatty acid is protonated by the acid catalyst. The protonated intermediate is then attacked by glycerol. A proton transfer occurs, which leads to the formation of a water group. Electrons on the oxygen move to reform the double bond, and the water is kicked off. The hydrogen on the oxygen is picked up, regenerating the acid catalyst, and the reaction is repeated 2 more times to form the triglyceride. So I finally reach 195 C, and I turn on my timer for 100 minutes. The solution is giving off a lot of white vapor, and at first I thought it was water, but I think it's something much worse than that. I don't really have a way to completely confirm this, but I think it's a combination of smoking fatty acids as well as acrolein from the breakdown of glycerol. So not only is it irritating to both the lungs and the eyes, but the smoking fatty acids are technically a fire hazard. Anyway, 100 minutes later, the reaction should be done. The moment it finishes, I take out the thermometer and I cover the top with some plastic wrap. The entire flask is then placed into a fridge for a couple hours. A few hours later, I pull it out, and I have this brown goopy liquid. This was really promising for me because I started out with fatty acids that were solid at room temperature, but now I have a liquid even at refrigerator temperatures. So at the very least, some sort of chemical reaction has occurred. To find out if I've actually made any triglycerides though, I'm gonna have to process it a little. The first thing to get rid of is the zinc chloride catalyst. Zinc chloride is very soluble in water, so it should be pretty easy to wash out. It's important to remember that this reaction is reversible, so when water is added, we could start to get some ester hydrolysis. At room temperature and with such dilute conditions, this shouldn't really be a problem, but it's still best to go as fast as possible. It was all transferred to a large separatory funnel, and then I waited for the layers to separate. The lower water layer, which contains the zinc chloride, is drained off and discarded. All of the oil is transferred to a small flask, and I set things up for a vacuum distillation. In theory, this can be done without a vacuum, but the temperatures required are much higher. I insulate the flask with a bunch of aluminum foil, and I crank up the heating. If I actually did make triglycerides in this reaction, the major one should be triolein. However, the boiling point of triolein, even under my full vacuum, is still above 400 C. There are very few thermometers that will go this high, and the one I have only goes up to 250 C. So because of this, I have to go without a thermometer, and it makes things a little bit more difficult. Instead of identifying different fractions based on temperature, I have to do it by appearance, which isn't going to be super precise. Anyway, the first thing that came over was clearly water, and this was followed by something that solidified immediately in the flask. Triolein and the other triglycerides that make up olive oil don't freeze at around room temperature, so I assumed this solid stuff was mostly just fatty acid. For a while, all of the stuff that I collected immediately solidified, but eventually, this yellow oily stuff started to come over. When it cooled down to room temperature, it still didn't solidify, so I started to get really hopeful that this was the triglyceride. Eventually, the oil stopped coming over even when I increased the temperature a little, so I stopped the distillation. In the flask, I was left with this boiling black liquid, which completely solidified when it cooled. Cleaning this up was a pretty big mess, and I'll show you guys that later in the video. This was the final yield of my oil, and it honestly looked really promising. To see if it is in fact triglyceride, I'm gonna have to do some testing. A simple way to test it is to use copper salts, usually copper acetate, but I only had copper sulfate on me. I made a concentrated solution of copper sulfate, and then I added a little bit of my oil. I quickly mix things around a little bit, and I wait to see if a color change occurs. Unfortunately, the oil very clearly takes on this green color, which indicates the presence of fatty acids. It doesn't say whether triglycerides are present or not, but so far it doesn't look promising. I looked around online a little bit, but I couldn't find a distinctive test that would actually tell me if I have an ester-containing compound. All the ones that I found would give a false positive if fatty acids were present, so in my case, they were pretty useless. Luckily, a very nice friend of mine offered to run an IR analysis. So I went over to his lab, ran a sample, and then proceeded to be sad. For organic molecules, IR analysis can help us identify the functional groups that are present. In this case, we're hoping to see ester bonds from the triglycerides, and we're hoping not to see carboxylic acids from the fatty acids. Both of these groups contain a carbon-oxygen double bond called a carbonyl, which is detected around the 1700 area. On my graph, I have a peak at 1709, so there's some sort of carbonyl present. To know which one it actually is, we can refer to an IR table with the standard values. So here's the carbonyl section, and we can see the ranges of each type. Unfortunately, carboxylic acids appear in the 1700 to 1725 range, so this is probably what I have. The range for esters is a little bit higher, and they're usually between 1735 and 1750. So this is a little bit sad because there's really no detectable presence of an ester. Based on this, I suspect that what I have is pretty much just oleic acid. I found an IR graph of oleic acid online, and the spectrums are very, very similar. One thing to keep in mind is IR alone is not enough to characterize a molecule, but in my case, it does seem very likely that it's just oleic acid. So in the end, this preparation was pretty much a failure. However, I think this might be the first and only time that a failure is just as good as a success. In my mind, the fact that it didn't work here really just highlights how hard it can be to go in the other direction. Making soap is super simple, and we just throw some base and oil together, and boom, we get our salted fatty acids. Going backwards, though, the process is much more involved, and it's clearly more difficult to get going. According to the paper I followed, this really should have worked, but for whatever reason it didn't. Maybe my fatty acids weren't pure enough, or my acid catalyst was a low grade. This paper is advertised to be used with waste fatty acids though, so I'm really not sure. Based on my recovery of fatty acid, most of it clearly didn't react, so it might be possible that a lot of the glycerol just broke down under heat. Anyway, all of this isn't to say that this reaction can't be done. The esterification of glycerol and fatty acids is actually done frequently in industry. However, they usually make mono or diglycerides because they have some unique properties. If I was really dedicated to get my triglyceride project going, I would have to tinker with a lot of reaction conditions, and I don't really think it's worth it. I could also try a different procedure, like the one I found here. Instead of zinc chloride, it uses para-toluene sulfonic acid as the catalyst, and it also uses THF as a solvent and molecular sieves as a drying agent. Some of you might be wondering how animals or plants do it, and it's a lot more complicated. At least in humans, this is the pathway that's used. It's not exactly something simple to just carry out in a flask like I tried in this video. Anyway, that's a little bit off topic, but if you guys are interested, I would like to cover enzymatic processes in the future. After it failed, I was pretty sad because I wasn't able to make oil for my French fries. However, I decided I would just do it anyway with the fatty acids. So I chopped up a potato, heated my oleic acid, and then tried to cook them. The amount of fatty acid vapor and acrolein that was being let off was pretty obnoxious. I had to wear a mask and keep things really well ventilated, or else my eyes would start burning. After cooking for a few minutes, I took them out and they actually looked pretty good. Despite how good they looked though, I knew they would taste horrible, so there was no taste test. As I mentioned earlier, the cleanup was a huge pain, and to get things out, I had to blast it with a heat gun. The footage here is kind of funny, and I don't think I have to tell you what I think it looks like. When I got out as much as I could, I let it sit in a base bath for about a week, and then I was able to rinse the rest out. Anyway, that's about it for this failure of a video. However, let me know what you guys think about exploratory processes like these, and if you'd like to see me post more in the future. In my last video, I had a contest to give away the soap that I made, and here are the winners. I've already gotten in contact with everybody and shipped out the prizes, but I'd like to thank everyone for participating. In the future, whenever I can, I'm gonna try to give away the things that I make or some souvenirs from videos. A big thanks goes out to all of my supporters on Patreon. Anyone who supports me will see my videos 24 hours before I post it to YouTube, and they'll also be able to directly contact me. Anyone who supports me with $5 or more will also get their name at the end of the video like you see here. In my last video, I asked you guys to submit music for my end screen here, but I think my intentions weren't super clear. I'm not looking for a permanent outro or anything, and I'm gonna be switching the music every single video. A lot of people have already submitted their music to me, and I'm gonna start including it as of the next video.